this nonlinear light curves could be described by the second and higher order perturbations of the stellar structure equations. And in curves, you can find, in 2015, you can find very quick and simple way of how second order perturbations can present or show combination frequencies, cross terms of the eigenfrequencies or harmonics of the eigenfrequencies as solutions of these of such equations. And but we don't know if these cross terms are really what we are obtaining from in our power spectra. So many research have centered their studies in trying to model light curves, meaning to develop a proper expression for the light variation, obviously considering limb darkening effects. But there is a direct, more direct way to model nonlinearities, which is by the Fourier parameters, meaning the amplitude, phases, and the frequency position in the power spectra, and modeling these parameters, which is the way we chose to proceed, since this is empirical study. And so the most simple way that two eigenfrequencies could interact, as described by the simple model, were two harmonic components with frequencies nu⁴ and nu⁴ we are going to call parent frequencies from now on, interact, giving it could be said giving birth to frequencies in these positions that we call children frequencies, with this phase relation and amplitude, this amplitude relation. For a mode coupling model, when any resonance conditions, like for example these ones, are met, we can model we can understand we can see on previously stable mode to become unstable when any of these resonance condition is met. And we could this couple mode, which is going to be very near the frequency value of a combination frequency, will have this way of modeling them, where but the amplitude it's described by this coupling factor. So yeah, as but in '96, Garrido first proposed this Volterra expansion to be suited to explain the nonlinear behavior of Delta Scuti star. It takes into it thinks of a star, of pulsating star, as nonlinear system, which the output, when the input are harmonic components, and in this case one harmonic sine wave, it could be sinusoid, the output could be described by this equation, where we can see that the system is completely satisfied when we know these gamma functions. These gamma functions, called the generalized transfer functions, accounts for the nonlinear processes happening within the star. And they are complex functions, so rearranging the equations, one can derive the amplitude and phases relations. Amplitudes are a function of the modulus of these complex gamma functions, and the phases are going to be a function of the argument this gamma function. So this is also the development for the output for a double mode variable star. And so yeah, now that we have set this this model, this general nonlinear model, one can start to identify the combination frequencies in the power spectrum. And we start doing this by exploring the frequency relation, which is completely known. No, the gamma function does not intervene in this relation. So, but let me just say for later on explanation that the gamma functions are now if we know them completely, we could, as I said, completely know this output, and now that is the aim, to characterize them. So now with the frequency relation, when we were studying this frequency relation, we develop a self-consistent method to extract nonlinearities or combination frequencies for pulsating star light curves. And we do this, as I said before, with the motivation of trying to match after removing, properly extracting the combination frequencies, to match the remaining components to the available linear model. And we do this with searching for the best parents and the children that originated by them, and fitting them in a nonlinear square fit. But the search for this best parent is the novelty of the method, and is done as I'm going to explain right now. First, we select a frequency. In our case, we select the highest amplitude frequency, and we in this case, for a monoperiodic star, we compute all the combinations with these parents. In this case, the harmonics, all up to the Nyquist frequency, and then with a smaller steps in the first interaction of the first order and of the order of magnitude of the first decimal, we now take this frequency as a parent frequency, and also calculate all his children, his harmonics, and so on, with these five around, or in our case, five. I mean, 3 or 4 steps around the first selected frequency. So now we have 5, in this case, 5 families of best of parents and combination frequencies, 5 families. So we fit each of these families, and the residual light curve. From the residual light curve, we calculate the variance of the residual light curve, and we keep the smallest variance value. Let's say that this is the frequency that yielded the smaller variance value, and so the second interaction starts with this frequency, and the epsilon goes smaller, so to the second order magnitude of the order magnitude of the second decimal, and so on. This is the schematic of when we deal with 2 modes, obviously minding that these do not overlap. And so that's why I say that this method is find the best solution because it finds the best parents exhaustively. No family of possible combination frequencies is left outside of the test. So here I show the results of such a search for monoperiodic Delta Scuti star. And here we see the minimum of the minimum variance, which points out to the independent frequency. Here we show the cascade of interactions, which we find it saturates in the 14 interaction. But we keep a conservative approach in this fifth decimal, because when we compute the O minus C method for a monoperiod for such a star, we find this uncertainty. So just to be careful, we keep this value. But anyway, we could see that with that value, we account for almost all the signal, explain almost all the signal with combination frequencies. This is the percentage of how much of the signal can be explained by that particular family. And here in red, we show the residual light curve, and there's still some contribution, but it might become from an amplitude modulation, which is very common. But the order of magnitudes saying that we explain almost all the signal. And this is the best solution for the combination family that explains the nonlinear part of this signal. So for double mode stars, we have interesting results too. This is a high amplitude Delta Scuti. And here, this is a result where after this proper extraction, where we extract simultaneously the combination frequencies family with the best parent describing the most of the signal. After such extraction, a new frequency structure that was hidden could emerge and possibly allowing to match with linear models. For example, here we have an even display, separation from the central frequency. So possibly maybe a rotational splitting could be possible, but this is the interesting result. And this is for low amplitude Delta Scuti, so multi-periodic stars. We also account for a lot of the signal with combination frequencies in this case, and also frequency structure emerged from such a proper extraction. So to summarize this first part of the work, we can say that the best parent method is essentially a standard approach of fitting sinusoids to the light curve, but it assures that is the best solution because of the exhaustive search of the best parent, and that it do not add information because we fit simultaneously all the frequency and which are the exact combination values. So it's not from a pre-whitening cascade and then with a posterior identification, but a simultaneous fit. And for monoperiodic stars, it achieves precisions equal to those achieved by the O-C method. And for multiperiodic and double modes, allowed to frequency structure to emerge. But what is obvious is that we cannot identify a combination frequency as a nonlinear effect just by their frequency relation. So luckily, we have other two relations to explore. Yeah, so remembering our Volterra expansion, we have these complex generalized transfer functions, and so from the Volterra expansion, one can derive a general phase relation, and for all the phases and general amplitude for all the amplitudes derived from this general nonlinear model. And when we separate as the aim is to characterize this complex gamma function, we have this. We separate the argument in the modulus, and we end up with this phase relation and amplitude relation. So as I said, the gamma functions accounts for the nonlinear processes happening within the star. So if we were able to find a set of stars where showing the same nonlinear processes within them, we expect these gamma functions to be similar as they represent the same processes. So, and this is possible with high amplitude Delta Scuti stars. We take this hypothesis that the combination frequencies of high amplitudes are from nonlinear distortion processes. So this is a very reasonable assumption, since first, because of these three arguments. First, there are many because of the high amplitudes of the parents, many detectable combination frequencies in ultra precise data, of course, is very unlikely to all be eigenmodes. Another important argument is that they pulsate in radial modes, so we are sure that the components that we choose as parents are actually independent modes, and more importantly, as mode coupling induce amplitude modulations. But it is very uncommon, but high amplitudes do not show this amplitude variability. So is supporting the assumption that we just made. So the motivation for doing this hypothesis is that we could we expect the gamma function to be similar for all high amplitudes, and in different form for other. For example, for modulation on instrumental origin, which are not a non-linear process or independent modes, but it will be in shape differently from resonantly excited modes, and that's what we expect, that these gamma functions will be different for each process, non-linear process. Here I show how could two frequencies could have very similar frequency structure as a rotational splitting, and maybe confusing some rotational splitting with a combination frequency. So With this in mind, we build this. We compute the best parent method to a set of high amplitudes and concretely to 17, and we calculate second order combinations, so it won't be so computationally expensive, and orders of the combination not exceeding the Nyquist frequency. So we build the phases differences and the amplitude ratios for high amplitudes. And I'm going to show the results for a case study so we can understand the plots that we're going to analyze from now on. And so these are the expected phases, positions of the phases that we from the calculated combinations, but this is the obtained ones from the observation. So we subtract from the observed the calculated one and obtain this, what we call the phase differences plot, the relation of the phases. And this is the argument of the gamma functions. The y-axis is from 0 to 2 pi, so it's a cyclic axis. So this is not really a discontinuity. 0 is the same as 2 pi. So yeah, just to note this. And for now, we just I'm going to address to harmonics and adding additions, because subtraction combinations show not a very regular pattern, although it is a pattern, but as the phase differences relation do not meet the commutative property, the pattern is not so clear. So regarding the sums and the harmonics and the ultra precise data available, we show how we detect all these combination frequencies for this high amplitude Delta Scuti star, and an inset to this first phasor of the plot up to the 8th order of combination is here in this inset, and here we can see how this interesting pattern showing the phase differences show this interesting pattern where are seemingly parables, or and the combination frequencies are subsequent. I mean, like this is 5F1, 4F1, 1F2, 3F1, 2F2, 2F1, 3F2, 1F1, 4F2, and finally 5F2. So this pattern, we wanted to check if this is repeated for other high amplitudes. And this is what we obtained for 17 high amplitudes. The argument of the gamma function seems to be decreasing with higher combination orders. And this tells us that each combination order, meaning that each argument, the argument of the gamma functions could take different values in a band but with increasing the combination order. So, for example, argument of the gamma function of order 2 are only restricted to the values of differences relation from 4.5 to 2 pi, and so on. Although there is obvious dispersion or in the pattern. It's important to note that 6 peculiar hats I extract from this plot. So this is with removing these 6 peculiar high amplitudes, which curiously, all of them that do not match the pattern have higher rotation values. Let's see, for example, these monoperiodic stars have high rotation values for a high amplitude, which are usually slow rotators. And we see how the pattern it's a bit like delayed. The orders are have a displacement, and this happens in all of these monoperiodic stars. And in the double modes high amplitudes have that I discard is when the parents do not meet strictly the period relation expected for these stars between the fundamental and the first overtone, which is related to rotation. I don't know how rotation could influence the phases, but this is very interesting and a matter of future work. But I extract them from the set, so I had this in the end for the phase for the first 9 orders of combination. So let's check the amplitude ratios for this high amplitude. We obtain very regular pattern again, so we want to check the 11 non-peculiar high amplitudes if they are also regular. So we obtain this result very linear for each order. And so when we have these results, we could almost see that they are independent of the frequency. So we could merge these 2 plots into what we call a template, or the template of nonlinear distortion processes, nonlinearities, or combination frequencies from nonlinear distortion processes template. So this template, when we see this, I try to develop some applicability to this template, so we could see how we try to check whether our combination frequencies from the low amplitude Delta Scuti stars we could identify them in their power spectra. So we build what we call the diagnostic plots, which are the phase differences and the amplitude ratios plotted over the template. And so we did this for 100 low amplitude Delta Scutis, and there's not always low amplitudes Delta Scuti have combination frequencies, but when for at least 10 stars, we have a matching matching the template, and so we can see that when we match this template, we could make some inferences, like for example that the combination frequencies of these stars are from a nonlinear distortion nature. And another important inference is that we could actually say that the parents of these frequencies are radial modes. This is very interesting inference because this may allow to the first possible use of combination frequencies to identify modes in Delta Scuti stars. And I will show you an example of such mode identification. So if we know if this combination frequency match the pattern, this is the phase differences, it's not the template, but we could see that this add an extra constraint to our mode identification when we could identify the parents of this when it matches the pattern, that these parents are radial modes. So we, from Stellingwer's period relations, we can derive this relation, and with to the observed combination frequencies and parents, we could also reveal that it possibly identified the F1 frequency with the radial mode of order 2, and the second frequency with radial mode of order 3. Another possible application is when the frequencies, combination frequencies, do not match the example. This is also interesting. What this tells us is that it could still be a nonlinear distortion, nonlinearity, but with non-radial parents, which this is this template of such situation is still unknown. And obviously, a non-matching pattern could be an instrument systematic modulating the spectra or an independent mode. But importantly, more importantly, is when we try to discriminate from a resonantly excited mode. So what I did is search for a previously known mode couple family, and this is the case of Breyer study in 2014, where he stated that F66 in his notation is most likely to be a couple mode with parents of F40 and F26, and so the same for F6, where it could be a couple mode of these are really two frequencies, so the summation of these two frequencies or the harmonic of one of them. And he did this by needing a condition of amplitude modulation on between of these frequencies, and also exploring the variation of each of these components to match the model of nonlinear, of the mode coupling model. So what we did is that we compute the diagnostic plot for this star, for these frequencies, and we confirmed that they are nonlinear distortion process and they don't match the pattern. So yeah, this is another possible applicability of this template. So to summarize this second part, we can say that the study enabled to empirically characterize the nonlinear behavior of high amplitude Delta Scuti stars, which was the question of this PhD. And this we do this by assuming that the combination frequencies in high amplitudes are due to nonlinear distortion processes. One can associate this gamma function to such processes. And with this study exposed the possibility of the first use of combination frequencies in intermediate mass pulsating stars for mode identification, possibility of doing this, or identifying the nonlinearity nature of, of a combination, the combination frequency nature. So the main two conclusions of this work is that, as I said, a proper nonlinear extraction of the power spectra could reveal frequency structure that match the linear models available, And of course, as I just said, the diagnostic plots after statistically straighten of this diagnostic procedure, which is a future work, it could be possible to identify the nonlinearity nature without the need of tracking the variation between all the signal components and or needing the condition of amplitude modulation. Of course, if we want to see or know the detail, the mode coupling, the interaction between these frequencies, Breyer procedure is more precise for doing this, but this could be a fast way of just quick discrimination. And as a future work for straightening this diagnostic plots procedure, we can build a bigger high amplitude catalog of spatial observations. So this template could be of a higher sample. Spectroscopic and time frequency analysis could help to also to identify the nonlinearities, and obviously the study of the physical meaning of these gamma functions, the describing the physics and the nonlinear physics will be very interesting to explore in future work. So thank you for listening, and I'm ready to take some questions if you have.
Thank you, Mariel. Thank you for the nice talk. So please go ahead with your questions. I think you have, you should have a button around there to raise your hand, right? I cannot see now the button, but it should be in the bottom part of your screen.
My screen.
No, this is for the people who want to ask any question. So please go ahead.
So if there's no question, I can use my steering committee privilege, if you allow me, Antonio.
Yeah, go ahead.
Yeah, I just wanted to know if you got the chance to work with the TESS working group 4 team and compare the analysis of the frequencies that they made for the first cycle 1 targets, and if you got the chance to compare and see if you had more information from the same signal or not yet.
No, not yet, but thank you for the great idea. So more future work, which is always nice to develop all this empirical work. It's great. Thank you for the idea.
Thank you, Rita. I think that Daniel want to make a comment or question. Daniel, go ahead.
Okay. I actually have 2 questions. The first one is perhaps a naive question, but I was wondering if the Volterra expansion allows for amplitude variability over time of the different components.
Yes, I'm guessing that this variability in time could have different gamma functions that we see for high amplitudes, which do not show variability of their modes or in time, not in frequency, not in amplitude. So possibly another template for other types of nonlinear processes, in this case, including time variability, could be found.
Okay, thank you. And my second question I was wondering how many of the Delta Scuti stars you looked at rotates rapidly.
The rotation values that I checked are in the first slide light curve from test in the paper of Vicky. And so there's no, I don't recall the exact number, but I am sure that for this high amplitude, peculiar high amplitude Delta Scutis is let's say high rotation speed for a high amplitude, which is, I mean, common to the thought of them no rapidly rotating. Anyway, the peculiarity in these stars, I extract them from the set, but as you see, they are not so different from the pattern. So it's something to explore later on. As I said, I don't know how rotation could affect phases, but it's just a guess, an initial guess.
Okay, thank you.
Thank you, Daniel.
Thank you, Daniel. I think that Vicky has a question, but before that, I have here found the button to raise your hand. Is just in reaction button below part of your screen. So that if you want to ask a question, please raise your hand so I can see you in the list of participants. Vicky, go ahead.
Yeah, thank you very much. And thanks for the very nice talk. Very interesting. I was wondering, maybe you could go to one of your slides, and I'm not sure which one it is, but it's where you show the, so in your paper, it's figure 3. It's basically the original light curve. So the Fourier spectrum of the original light curve versus, and then you fit basically certain frequencies, and then you say that you end up with a structure that, yeah, I think it's this one, yes. Sorry, I have to get it. I'm a bit blind here. It's exactly this one here. So I wonder how the resolution of your data, basically, so how long you observe, affects these results, and whether you try to inject artificial signals into your data that sit exactly on those nonlinear modes to see if you can actually extract them.
Yes, the resolution of this light curve, I always use, when available, short cadence, like 1 month length observation. And for this particular result, high amplitude, just 1/4 of Kepler observation. And with this is enough to just to see these frequencies. And when I did a test of, if I understood correctly, you asked me if I did a test to check whether I find the combination frequency, artificial combination frequencies in a
no, what I meant was more like, so I'm a traditional frequentist, if you want to put it that way. Yeah. And when I extract peaks, I look whether, I can resolve them from the data, right? So and these peaks for me, so in this plot you show here, the blue one, I can see that there is a structure to your peak at, I don't know, 5 or just below 5 cycles per day. But the point is, when I extract that with traditional methods like fitting, a sinusoid, then you influence the signal, everything that is on top of that, right? Because if you have a specific resolution, you cannot get more information out of it. So I wonder to what extent those remaining peaks that are in the red plot, so on the top plot, are actually, so their amplitudes and their phases and their frequencies, to what extent they are influenced by your fitting procedure?
Well, the remaining peaks are not combination frequencies.
That's fine, yeah, but just their values. If you can actually really how well can you determine those values?
These frequencies are resolved and detectable for if I understood correctly your question, with an regular
Fourier analysis.
Amplitudes detectable from the noise. So in a power spectrum over 12 power value, 12, around 12. So if these peaks are over 12, which they are, I consider them to be
yeah, okay, so you said that the signal to noise is high enough, but you should also, I think, take a look at whether they are really resolved. It's 1 over delta t, right? Delta t is the length of your observation.
Yes,
and whether
I don't have 2 peaks inside one.
Okay, that was the question. Okay, thanks.
I'm sorry. Yeah, I don't have this. It's not that dense power.
Okay. All right. Okay, thank you.
Okay, so we are going to have one last question by Jordan. Jordan, go ahead.
Hi. Hi, Mariel. Thank you for your nice talk. I'm working on deciphering nonlinear mode coupling in gravity modes of B stars. So I was wondering whether your Volterra expansion method is equally applicable for gravity modes, for example.
Yes, actually, this presentation is focused on Delta Scutis, but I've been working on applying this technique with to gamma door stars, and very interesting results have been having with this procedure and this Volterra expansion, because the amplitude relations and the phases differences also form patterns, which I'm currently studying. And also a very interesting topic is that differences are also in this case with G modes, where as the frequency distribution it's mainly below 5 cycles per day. This small amplitude, small frequencies terms which are captured with the subtraction combinations do follow a pattern, and I see a pattern, and with the subtraction combination. So it's still a work in progress. Hopefully, maybe we could, work on that together, because probably you know more about the gamma door and G modes. So we could understand these plots and these templates. I need some help actually to understand them, these new patterns for G modes.
Okay, well, that sounds very interesting, and I'm looking forward to it.
Great.
Thank you.
Thank you, Jordan. Okay, if it is very quick, we can have a very last question by Thomas. Thomas, go ahead.
Thanks. Just this is a bit of a naive question. You mentioned that we could use this template to say if the frequencies follow the template, we could say that these modes, the parents of these modes, are actually radial modes. But while we do not know the templates for non-radial modes, how can we unambiguously say that this is indeed the case?
When that they are not from a nonlinear distortion process, you mean?
No, they could, when the templates for non-radial parents
Yeah, we do not know how the shape of this template. So we only have a template for when this template it's valid for high amplitude delta scuti, what they are, and they are usually pulsating in radial modes. So we could safely or reasonably assume that this template is for radial parents, and we do not know the shape of this template if the parents are non-radial. So when I mean with unambiguously is when the unambiguous identification that I meant is combination frequencies from radial modes from nonlinear distortion process.
Yeah, but that's the point when I mean, from non-radial modes, the template might look exactly the same. As long as we don't know it, we do not know that it doesn't look the same. So we cannot use it to say that if it fits the template, it must be, it has to be a radial mode, or the parents has to be radial, right? We can just say we have hints.
Well, it's just an hypothesis. It's based, what I say is based on the assumption that, as I said, had high amplitude. This is only high amplitude stars, so that are usually pulsating in radial modes. So if there's a possibility of high amplitudes to pulsate, one of these that do not pulsate in radial modes, but in non-radial modes, we expect them to be somehow different, and yeah, I understand now. What I think I get it. That non-radial. Did you mean the non-radial modes from parents whose combination frequencies will match also this template or not?
Well, in principle, it could, right? We don't know if they might end up having the same template then, right?
Yeah, we don't know. So, but the hypothesis is that this is built for a high amplitude delta scutis, which commonly are known to be pulsating in radial modes. So our conservative approach is to just remain in this hypothesis for radial parents, and we don't know the template of non-radial parents, because
okay.
we don't have a set of stars where we are sure that the parents that we are using as again as parents of our combinations are radial and non-radial.
Okay, I think this is an interesting discussion, but maybe we should stop here. And you can contact Mariel Thomas by email if you want to talk to ask anything. So thank you, everybody. I return the floor to Rita. Rita, I think she wants something to say.
Yes, well, thanks a lot, Antonio, and thank you, Mariel, for a very interesting talk and with solid work. So I refer you to our website, the Good Vibrations seminar series website, where you can find more information and contact information also. Thank you very much, everyone, for attending, and I wish to see you in 2 weeks from now for Martin Farnir, getting back to solar-like pulsators. Thanks a lot. Maybe the steering committee could stay around. Thanks.
Thank you.
Bye, everyone. Thanks very much, Mariel.